All right, thank you for the opportunity to present here today. And I realize I'm the last speaker before the break here, so I'll try to be brief here and have time for questions. Right. So I'm going to be talking today about machine learning opportunities, science opportunities with the SAIL campaign. This is really the results that I'm going to present are based on work that a number of colleagues at Berkeley, Berkeley Lab and UC Berkeley have done so far. But it really would like to get your your feedback, your thoughts, things that you would like with this campaign. A little bit of background for those of you who are not familiar with SAIL. The Surface Atmosphere Integrated Field Laboratory is an upcoming mobile facility campaign, but its motivation is built on the fact that about half of the world's population depends on water resources that are derived from mountain systems. These resources, at least in across the Western United States, have been dwindling over the last few decades. This shows the map of the snow water equivalent change that is measured by the network of surface stations called SNOWTEL stations across the Western United States, and we can see that most of these stations show decreasing amounts of snow water equivalent, and this forms the basis for a large amount of the water resources that our water systems derive, so we need to understand we have the capacity for being able to project what these changes might look like in the future. Do they, are they essentially, do they have a proper instrumentation? Do they have the representation of processes that we need to understand these trajectories, because they have major societal implications? A survey of a number of models of different levels of complexity indicates that there's a wider level of variability. On the left, we can see the projections of the Western United States snow water equivalent anomalies for the middle part of the 21st century for a variable resolution run of a climate model. In this second to left is a statistically downscaled set of projections from the last version of CMET5, a regional climate change analysis program set of changes for the same period, and then the raw climate model output from CMET5, and they show pretty wide changes in snow water equivalent for across the Western United States, depending on which version of either downscaled models or that you would like to select. And with the parent models, deficient performance in terms of their projections of snow water equivalent. This suggests that the details really do matter for what is leading to the changes in this quantity. And this has in part motivated the deployment or the future deployment of the SAIL campaign. This will take place between September 2021 and June of 2023, and will occur in the upper Colorado River in the Rocky Mountains, and will include the AMF2 package and precipitation radar from Colorado State University. In a somewhat unique way, this campaign will include the co-location of observations and analysis between ARM capabilities and those of an program, watershed, an existing measurement campaign called the Watershed Function SFA that is being supported by the SBR program. And ultimately, we're looking to determine really the amount of atmospheric process fidelity that we need to predict water outputs from these mountainous watersheds. SAIL's focus on a number of different processes that impact upper Colorado River hydrology, including precipitation, trying to understand what's governing its variability in amount and phase, and why and how we're seeing that variability, what the processes are that are contributing to that. Looking at wind sublimation, the snowpack and how it redistributes snow, and taking a hard look at the way that aerosols impact this this area, and both in terms of impacts on radiation and precipitation within the atmosphere and at the surface, and looking at the various controls, radiation, sensible and latent heat, primarily, and on the surface energy balance. So the campaign will include the AMF2 package, as I mentioned, includes about almost 3 dozen instruments measuring precipitation, clouds, winds, aerosols, temperature, humidity, trace gases, and surface fluxes. And this, in addition to a precipitation radar. We're looking to measure, as I mentioned, in the Upper Colorado River area. The instruments will most likely be within this East River watershed here, which is a 300 square kilometer area that is part of this Upper Colorado River and the Colorado River Basin, which is 640,000 square kilometers and serves about 40 million people. This is a heavily instrumented site already from the Watershed Function SFA, and provides context for the observations over for the past several years. This is a perspective view of that watershed. It is roughly a bowl. On the southern side, there's a Crested Butte Mountain, where we're looking to put a precipitation radar, sort of near where that X is. And that will kind of survey over this area. There's another X where this is another SNOTEL station that both of these will measure snow water equivalent as reference points. And then we're looking to put the most of the AMF measurements, AMF2 package, up in Gothic, which is kind of in this valley here, about 10 kilometers up the valley from this mountain. The SAIL science team covers 4 national labs and 10 universities and 2 research centers. So I've had the privilege of working with them to stand up this campaign, and we have expertise in precipitation, aerosols, land-atmosphere interactions, snow, and radiation processes. When it comes to machine learning, though, I'm really excited to present at least some of the results that we have over this area, but really want to talk about these results within the context of proceeding with caution. I'm really intrigued by the advancements that ML has made in the last few years, particularly working with the types of messy problems, language, image processing that we've really seen dramatic advances of lately. Within the realm of geosciences, though, it's, at least for me, it's been I've had to scratch my head and try to think about how to use these tools properly. And I think there's some opportunities to do so with the SAIL campaign. This is a little bit of a flip diagram that I've shown here regarding the technology development, and I feel like we're moving towards this this slope of enlightenment here. And I'll present a couple of examples that hopefully can convince you that that's where we're going. The first, with respect to SAIL, I think there are kind of 2 principal ways that we can think about this, but really would like your thoughts on others. The first is to use the SAIL data for machine learning model testing, which I think is a relatively straightforward, at least at the start. We can think about this, for example, with using SAIL observations of precipitation to test machine learning downscaling methods for precipitation, that recognizing the fact that precipitation in mountainous systems is highly heterogeneous, and the fact that observational products are based on observations that do not capture all of the heterogeneity, and therefore the these observational products have to basically process information in order to provide the proper fields to drive hydrological models. The ExoSheds project is something that is just starting up at Berkeley Lab, and it's seeking to develop models of the Upper Colorado River water system without sacrificing process fidelity, and and is trying to wrestle with the fact that the precipitation data are either spatially or temporally sparse and under-resolved. This is of interest. These plots show you know, the watersheds that the Exosheds project is seeking to measure and model, and a number of the station observations over here. And here are the labs and universities that are participating in the Exosheds project. In terms of for model testing, there's been some development already for the production of a random forest methods to impute missing high spatial temporal resolution precipitation data based on sparse data sets. And we can think about these model with precipitation observations. That hasn't been done yet. The imputation with random forest data, that machinery is up in place, but the sail precipitation radar observations are not. And so when those become available, I think we can do that. And when we do that, we may see some disagreement. And then I think there'll be some head scratching, and we'll have to ask some hard questions. But some of those questions that we can ask have to do with the, if we're able with these methods that have been developed to capture the spatial and temporal correlation patterns that are observed in the data. And then we can also think about developing methods or thinking about if these methods are unbiased in their forcings for hydrologic models. And if they're not, why aren't they? Are there processes that the machine learning methods are not capturing within that, within the spatial temporal correlation patterns, maybe that they're not able to capture, and then we can interrogate them further or evaluate if different methods are able to really capture that. So that's something that I think model testing is straightforward to do, and I look forward to doing that with the Exosheds team. There's also another application, which is model emulation. For immature physical models, I think machine learning model emulation has some really useful features. We can use these model emulation because it's extremely computationally efficient, and that gradients within the emulated model are inexpensive and easily calculated. It's very difficult and computationally expensive to calculate gradients of physical, of process models, but it is relatively straightforward with machine learning models, and we can use ML model emulation to understand physical models and their errors. I'm showing here one application with a generative adversarial network, or a GAN, and this is designed to prevent overtraining and physics constraints. So this is one type of emulation that we can do. Here I'm going to talk briefly about a physics constrained GAN. These GANs try to optimize along a loss function, and then you can create a physics constraint and achieve simple with a simple regularization of the optimization loss function, which is shown down here. Some of these can be relatively straightforward, having non-negative precipitation, or you can include many more terms, and then there are some questions about how you set alphas and betas for your loss function using the statistical constraints, but that's sort of the general structure here. We've put something together for snow water equivalent based on for California precipitation. We used a number of predictor variables, temperature, precipitation, radiation, winds, and we were able to train this GAN model to emulate snow water equivalent behavior across multiple time and space scales, including a number of zero values that we have of snow water equivalent across this domain. And we're also able to use these gradients that were calculated from the GAN to understand the relative importance of atmospheric forcings to the scale of our output. So we're able to do these things called ablation studies, where we take one channel, one variable, and fix it or remove it from the training, and these we can do this sequentially and together, and we can identify the relative importance of input variables to the GAN, and this helps prioritize process studies. And we can look at this across seasons and see, across seasons, which of these variables matter the most, and these are kind of these seasonal variables of the importance of these variables for snow water equivalent. So I know I'm really short, so thank you for the opportunity to present here today. Very briefly, we're looking forward to doing machine learning with SAIL. We will have lots of data, and I just presented a couple of different examples of what we can do, but we'd really like to get your feedback and ideas on where you think ML methods can be used as part of the SAIL campaign.
Thank you, great talk. So I saw one question so far. So surface roughness length is often the variable that moves around SMB the most. Is this measurable in SAILs?
So yeah, that's a great question. So there are some ways that we can think about measuring that. So with the SAIL, with the AMF2 package directly, that will be a little bit more difficult, but there will be aerial campaigns to collect data. There have already been very detailed maps of the of the distribution of vegetation across the area, and there will be aerial surveys of the snowpack throughout, either basically snapshots, and then you could sort of basically pull out that quantity from those, but it will be sparse. It will be under resolved. So I think there's definitely some. This is not an unlike the sort of language and image processing we're under resolving here. So I hope that helps answer that question, at least in part, and like to follow up more though.
Okay. There was another question in the chat somewhere that disappeared for me. But in particular, can machine learning be used to downscale precipitation in the ablation zone? Elevation classes similar good enough at filling in precipitation?
Yeah, I mean, that I think is I hope that is the case. I think that can certainly be something that can be tested with with the observations, and we could do those kinds of studies, and I hope that either people on this call or outside will be able to do that.